Hey all, Professor Marinos again. And in the last lesson, we described some properties of water that make water special and important for geochemistry. And one of those properties that we discussed was that it can dissolve polar molecules. It's a polar solvent. And so today we're going to launch into a discussion of what it can dissolve. This is our tour de force of solutes of the world. Okay, so by the end of this video, what I want you to be able to do is to describe the principle of charge balance and to be able to list the major solutes in environmental waters. So this is a figure from Brzonik and Arnold, the textbook that I like to use, which is a cumulative frequency distribution for inorganic solutes in the waters of the United States. So what does that mean? Well, on the x-axis of this graph, you have parts per million of solutes, or milligrams per liter, as you know. And you notice that this is on a log scale. So over the linear space here, it goes from 0.1 to 1 to 10 to 100 to 1,000. So this is a log linear graph. And on the y-axis, you have the percent of surface waters that have less than a given amount of solute, as indicated on the x-axis. So you can read this graph by saying, like, what percent of waters have less bicarbonate in them than 100 parts per million? So you come to bicarbonate here, HCO3 minus. Look at 100 parts per million, draw a line up, and then from here, go over to your y-axis, and you can see that 20% of the surface waters in the United States have less than 100 parts per million of bicarbonate. You can also do this for calcium. What percentage of waters have less than 50 milligrams per liter calcium? Come up, come over. You can see that about 55% of surface waters have less than 50 parts per million calcium in them. And this is a really useful figure because not only does it show what are the most common solutes in water, you can just kind of read across here, you see bicarbonate, calcium, sodium, sulfate, chloride, silica, magnesium, potassium, nitrate are the most common. But you can also see the range that's exhibited. So you can see, for instance, silica has a rather tight range. All the surface waters of the United States are somewhere between 7 and 50 parts per million silica, whereas something like nitrate has a relatively wide dynamic range. You go from 0.1 parts per million all the way to 10 parts per million. So that's a change of 2 orders of magnitude, whereas silica is less than 2 orders of magnitude in total. So this figure is a nice kind of summary of the major solutes that you see in waters of the United States and how much variability there is in those. And again, the major elements are, or the major solutes are bicarbonate, calcium, sodium, chloride, sulfate, silica, magnesium, potassium, and nitrate. So that's a big laundry list. Okay, so now let's talk about where these solutes come from. And you can really learn a lot about water by what solutes are in it. Solutes tell the story of water. Solutes tell you what minerals and what organisms this water has been in contact with and for how long. So you can really learn a lot about the history of water just based on the chemistry of water. And so I've divided solutes into 4 major bins of sources. And the first one I want to talk about is geogenic solutes, or solutes that come from rocks. So at the top of this list we have silica, dissolved silica, and this shouldn't surprise you. Most of the crust of the Earth is made out of silicate rocks, so dissolved silica just dissolves from those rocks and creates silica in environmental waters. The next class of elements I have here are these cations, calcium, magnesium, sodium, potassium. These are pretty common environmental solutes, and these are also rock-derived. Calcium and magnesium, for instance, from dolomite, dolomitic limestone, calcium carbonate, magnesium carbonate. Sodium and potassium are found in feldspar, as an example. These are just examples. There are tons of minerals that bear these elements. But these minerals dissolve and just release these cations into solution in waters. These cations are often paired with various anions like chloride, sulfate. Sulfate comes from minerals like gypsum. Bicarbonate is formed by the dissolution of calcium and magnesium carbonates, as an example, or limestone, the dissolution of limestone. And last on this list, I have phosphate, which is actually a very, very trace solute in most waters, but it's super important for life. This comes from minerals like apatite, fluorapatite, hydroxyapatite. minerals that are super, super important for life because they bear these very, very tiny amounts of phosphorus, which is a key element that sustains life. So even though this is a trace element, it's super important, which is why I put it on this geogenic list. Now, the next class of solutes I want to talk about are atmospherically derived solutes. We have, top of the list, oxygen. You know, the atmosphere is 21% oxygen, and that oxygen diffuses into surface waters and supports life in those waters. It supports aerobic life in waters. So the input of atmospheric oxygen into waters is a vitally important process. Secondly, I put sulfate on here. You'll note that sulfate is also on the geogenic list, but it is also atmospherically derived. The major natural source of atmospheric sulfate is volcanic eruptions, which release sulfur dioxide into the atmosphere, and that rains down on the landscape as sulfuric acid, which contains the sulfate ion. Finally, we have bicarbonate on this list. Bicarbonate also is on the geogenic list again, but the atmosphere contains over 400 parts per million carbon dioxide, and that carbon dioxide in the atmosphere also just dissolves into water where it forms a bicarbonate ion. So bicarbonate can be either atmospherically derived or geogenically derived, depending on where you are. So moving on, now we'll touch on biogenic sources of solutes, or solutes that come from life. Again, we have bicarbonate on this list, so bicarbonate makes its appearance in a lot of different places. Now, how is bicarbonate a biogenic solute? Well, again, the key is you breathe in oxygen and you respire carbon dioxide, like all organisms do that have aerobic metabolisms. And if you're doing this underwater, then you contribute, by exhaling carbon dioxide, you contribute this bicarbonate ion into the water because carbon dioxide forms carbonic acid, which then dissociates to become bicarbonate, which we'll touch. That's a process we're going to touch on a lot. But so, for instance, around tree roots respire, and if those tree roots are sitting in water, you can have concentrations of bicarbonate that are much, much higher than would just be expected from atmospheric diffusion of carbon dioxide into that water, like orders of magnitude higher, 10 or 100 times higher. So this is a vitally important pathway, this biogenic pathway by which bicarbonate ions can get into water. Next on this list, I have nitrate. Nitrate is made out of nitrogen, and nitrogen is an essential element for all life. And so microbes have derived mechanisms of taking atmospheric nitrogen and converting it into a form that they can use, which then eventually becomes nitrate in surface waters. This is the same story with ammonium. Ammonium and nitrate are both forms of bioavailable nitrogen that organisms can access and that they produce to put into surface waters. And finally, the last thing I have on the list is organic acids, which are super important for the acidity of surface waters. These are compounds that arise from dead and decaying plant and animal matters that are converted into these soluble organic acids. And finally, the last thing that I want to put on our list, the last bin, are anthropogenic sources, or sources that come from humans. And a lot of these we've already touched on already. So we have nitrate at the top of this list. Nitrate is an exceedingly important agricultural fertilizer. We said again that nitrogen is essential for all life. And so humans make a ton of nitrate fertilizer from atmospheric nitrogen using a process called the Haber-Bosch process. And we put it on fields. That nitrate fertilizer dissolves, it ends up in our waterways and causes a lot of nitrogen pollution. So a major source of nitrate in the waters of the world is from humans doing this. Sulfate is another important source, although it's becoming less and less important because of pollution controls. But we burn a lot of coal, we burn a lot of gas. Those things contain sulfur in them, and when we burn those fuels, they release sulfur dioxide into the atmosphere, which again rains down on us like as acid rain. So you have sulfate both as an atmospheric, a natural atmospheric source, and as a very strong anthropogenic source of solutes as well. Finally, we have phosphate, which we had on our geogenic list again. But phosphate is, again, a very important element for life, and we apply it as fertilizers to fields. And so we have a lot of anthropogenic phosphate that comes into our surface waters via application of fertilizer on fields. Now, all of this fertilizer is ultimately rock-derived. It's just mined and then applied on fields, so you could call this an or a geogenic source. But I think that the magnitude to which humans have moved around phosphorus on the Earth makes it deserving of being called also an anthropogenic solute. So I said that solute chemistry tells the story of where water has been. And I just want to give you a brief example of this from a small creek in Tennessee, which I think is a real nice illustration of this property. On the x-axis of this graph here, you have sulfate concentration in water, and on the y-axis here, you have calcium concentration. And these black points on this graph indicate the chemistry of different pools of water that existed in the watershed surrounding this creek. So down here, you have unsaturated surface soils, what the water chemistry looks like. It's very high in sulfate, very low in calcium. Over here, you have the water chemistry that they measured from saturated soils. You can see it has low calcium still, but significantly less sulfate. And then up here, you have the chemistry of the groundwater that you see in this watershed, which is very high in calcium, very low in sulfate. This is a limestone underlain creek, so no surprise that there's a lot of calcium dissolved in the deep groundwater. And these white dots here, which you can see over here, illustrate the course of the water chemistry throughout a storm event. So this is before the storm began, and as the storm progresses, you follow these arrows, and then this is right here is the end of the storm. And so what you can see here is before the storm begins, the flow of the water is very high in calcium and low in sulfate. And this is an indication that all of this water in the stream, when there's no storm, so at base flow, is coming from deep groundwater. Then, as the storm picks up and water starts flowing, the water gets less and less rich in calcium and more rich in sulfate. So it's moving towards this unsaturated surface soil end member here. These black points we call end members. And so this is indicating that more and more of the water during this storm event is coming from these unsaturated surface soils. Finally, as the storm ends, you have the calcium concentration increase and the sulfate concentration decrease, but it's less than you had originally. And this kind of indicates that the water is coming from a variety of sources, both from saturated soils and from the deep groundwater at the end of the storm event. So at the beginning, you have groundwater-dominated flow. In the middle of the storm, you have surface soil-dominated flow. And at the end of the storm, you have a mix of saturated soil and deep groundwater contributing to the flow in this stream. So I think this is a really nice example of how just two solutes, we have calcium and sulfate here, can really tell a very compelling story about where water is coming from and what water is doing. So we've just been discussing a lot of different... 1, 2, 3. So we've been discussing a lot of different solutes that are ions. That is, they bear either a positive or a negative charge. They're either cations positively charged or anions negatively charged. And this brings me to my next point, that waters are electrochemically neutral. Despite what some health waters would have you believe that advertise that they've had all their negative ions removed. That's impossible. You can't remove all the negative ions from water. That's bunkum. Anyway, I'm off on a tangent. It just drives me nuts. Waters are electrochemically neutral. They're never going to have a net positive or negative charge associated with them. And so what this means in practice is that if you take a cation, wrong side. If you take a cation and you determine its molar concentration in water and multiply it by its charge, and you do that for all the cations in a water sample, and you sum them up, so the sum of all the moles of cations multiplied by their charge, this must necessarily equal the negative, because anions are negatively charged, sum of all the moles of anions multiplied by their charge. So what does this mean in practice? So here are the major ions in surface waters. I've included these geogenic ions, sodium, potassium, calcium, and magnesium, and I've included hydrogen here. You'll note hydrogen is a product of acidity, and when acids dissociate, they produce hydrogen in solution. We're going to touch a lot on that later in our acid-base chemistry, but just note that this is potentially an important term for charge balance, particularly in acid waters. Anyway, we take the concentration of hydrogen multiplied by its charge, 1, add this to sodium multiplied by its charge, blah, 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 hydrogen, sodium, and potassium are +1, calcium and magnesium are +2. The sum that you get here must necessarily equal the sum of all your ions. So I've included on this list nitrate, a biogenic and anthropogenic solute, sulfate with its charge of -2, bicarbonate, -1, chloride, also -1. If you sum all these up, these two should equal each other. Now I've also put down here DOC. What is DOC? DOC is dissolved organic carbon. This is stuff that comes from plants. These are organic acids that have their protons, which are accounted for over here with these pluses, dissociated from them. So the conjugate bases of organic acids result in solutes that have negative charges. So this DOC has a negative charge, but it's exceedingly hard to quantify exactly what that negative charge is. So this kind of causes a problem in our charge balances that can be appreciable or not. So there's kind of a rub here. But generally you can assume that these two are going to equal each other. And this DOC term will only become important in waters that have pretty high concentrations of DOC. So I just said that it's very, very hard to know what the charge of DOC is, and that's because it's very, very hard to know what the structure of DOC is. So this is a crazy, carbon molecule that you could see dissolved in water. This is a humic acid. And you have all these crazy aromatic domains, you have all these crazy aliphatic domains, you have all just a very, very complex chemistry. And this is one of a near infinite number of possible chemistries that you have for dissolved organic carbon. And over here here's a carboxylic acid group, and that could contribute a negative charge if this proton gets kicked off. You have some phenolic groups that could also contribute a charge if one of these protons gets kicked off. But it's super hard to know what the net sum of these charges are going to be on the surface of this organic carbon molecule. And like I said, this is one of a near infinite variety of dissolved organic carbon molecules that you could see in solution, giving a solution charge. So this is why there is a big question mark on what that charge was. So what can you do with this? Well, one thing that you can do is you can just say, well, I'm going to do my charge balance. I'm going to balance all the charges that I can measure from my inorganic ions like potassium, magnesium, sulfate, nitrate, those things. And then whatever is left over, because I know that the principle of charge balance must be operating, I can attribute all those remaining charges to the charge that's on dissolved organic carbon. So that's one approach to dealing with charge balance. And what charge balance can actually tell you, charge balance can be used as a metric of what the total charge of dissolved organic carbon is in solution. Another thing that you can do is you can calculate charge balance error. And this is an indication of what the completeness of your water chemistry analysis is. So if you sum all the moles of cations multiplied by their charge and subtract the sum of the moles of anions multiplied by their charge, and then divide this by these two same sums added together, this gives you a relative amount of error in your charge balance. So if you have a 10% error in your charge balance, that means that you are not accounting for some amount of cations that you didn't measure. So say like you didn't measure magnesium because you didn't think it was important in your water chemistry, but then you come up with a big charge balance error of 10%, you can be like, oh, I need to go look at some other solutes. Maybe I'll measure magnesium. Maybe I'll measure, some other crazy one like strontium or something. Maybe that's making up my charge balance. So charge balance error is a good indication of the completeness of your water chemistry measurements. Now it's important to note that you can either use this to estimate the amount of DOC that's contributing to anion charge, or you can use it for calculating the relative completeness of your chemistry analysis. But you can't use it for both because then you're solving, you're trying to solve for two variables using only one equation, and that just doesn't work out. So anyway, that's a brief summary of what charge balance is, why it always applies in water. Charge balance is an operating principle that will never be violated, and some things you can do with charge balance. You can estimate the charge contribution of DOC, or you can use it to estimate the completeness of your water chemistry analysis. by charge balance error. So that's all I have for you now. In the next lessons, we're going to talk a little bit about what the materials are that water interacts with to give us these solutes. We're going to go a little bit more in depth about soils, about rocks, about organisms, about people.